for having me. It's quite an honor to be among so many distinguished and expert scientists, artists, architects. Really quite an honor. The questions have been profound to me. I know a little bit about computing. I know a little more about drawing. I know absolutely nothing about the brain except for the fact that I have one or I am one, or kind of neither of those things. I want to start by listing some of my operating principles. Put this somewhere else. The first is that drawing is a space for research about architecture. That's kind of an important one because I think not all drawing is architecture. And drawing can also be relevant to architecture, even when it's not architectural drawing. Drawing is a kind of computing, coding, and mark making work well together. I do want to point out here, I say coding in this because I'm talking about the algorithmic thinking, right? The rules and the logic inherent to computer programming, and also the actual execution in a programming language. I don't say programming only because in the discipline of architecture, that word is already claimed by something else. So I use the verb coding there. A line in a drawing is always simultaneously one-dimensional, two-dimensional, and three-dimensional. I'm totally with Tom Mills on the importance of the 2D, 3D. The 1D really comes in terms of computation and mathematics, the ability to think about a line as a kind of parametric one-dimensional space. Representation is not about showing, but restructuring for the purposes of operation. That's kind of a more computer science definition of representation. Finally, computational models of drawings, in other words, like AutoCAD drawings, are not drawings. A drawing is not a model. It is primarily operated on by the eyes. And in that way, coding and mark making are inherently opposites and contradictory. And so yes, I've got two operating principles that are directly opposed to one another. I teach at RISD. In fact, I was hired at RISD to teach in this collaborative series of courses that was the result of a curricular restructuring where they removed the digital representation course and the manual representation course and decided very smartly that it made very little sense to think about the digital independently of the manual, which is a horrendous word, actually just as bad as the word digital. So in these courses, we think about the visual perception, the model, and marks in a kind of fluid space. So there really is never a moment where something, a mark or a perceptive artifact doesn't get sort of pushed or teased from one kind of space to another. So a line that is operated on in 2 dimensions is pushed into 3 dimensions and operated on in a different way. We're very directly connected to this idea that a line can be pushed into material capacities, whether through things like cut lines or actually fabricating the line. We do everything in the first semester that is architecture except buildings. And this is for Will. The second semester is exclusively about buildings. We don't call it a case study because the word case study would be too weak for what we do. It's the whole semester of nothing but analysis of one building project. So in this case, it's a very deep and profound question of how do you draw the entirety of a building project on one piece of paper. That's it. Basically, that's the brief that constitutes the assignment. And the digital counterpart is really not a digital drawing. It is really not about digital operations to produce lines on paper. It's about the idea of a model and the way that you can operate on a model differently than how you can operate on a drawing. So I want to start with and linger on for a minute this relatively recent drawing by one of my students this semester named Chigo. And To be honest, I could spend the next 25 minutes just talking about this drawing. There's a lot in here for me, and I hope there's just as much in here for Chi. But this is a drawing assignment that, and the structure of this semester's studio is that we're not just drawing to make buildings, but we're drawing on buildings and with buildings to unmake buildings, to see buildings differently, to operate on them. So this is a drawing that takes as its source material information that is three-dimensional, but then operates on it, writes computer code to think about how those lines exist on paper. And this is multiple layers of paper that have been cut. And this is produced by one of those aforementioned pen plotters. You can see, there's so many good moments, but see that extra kind of point-looking thing? That is because these are felt tip pens, that is the moment when the pen plotter pauses. So there's a component of time. It may not be time in a kind of fourth dimensional sense, but there is speed is inherently and directly related to the quality of the line. The start of the line looks different than the end of the line. And none of using a pen plotter is at all like saying file print or file plot. This is where their vintage becomes really an asset, because the price of admission to these marked lines are lines of code that describe or instruct them. I'll talk more about that later. But also, well, yeah, this drawing has everything. It has a way to read these lines as objects, a way to read these lines as surface, a way to read these lines as flat, a way to read these lines as surficial extrusions. So there was an animation playing earlier that was a kind of representation of a very simple drawing rule that says, draw a squiggly line. This is very much inspired by that Paul Klee quote, multiple Paul Klee quotes about active lines. I'll talk about that more when I get to a student project that's based on the active line. But these circle spheres, and that title basically says it all. There's instructions for a line that leaves a trail. So this is the line going for a walk, except the line is a dashed line. And that line is treated as a physical thing, and as it's taking a walk, the trail it leaves is like a fence that it cannot cross, except because it's a dashed line, that fence has little openings in it. So, and over time, as it's sort of driving along like in a car with a steering wheel, it can steer more aggressively so that it does not hit itself, because it's sort of a little bit looking ahead. Gradually the line turns from red to blue, but this is a one-line drawing. Turns from red to blue, and earlier moments of it kind of trap later moments of the line, and spherical conditions start to be read in these drawings. This is another run with the same rules. This one got trapped a little bit harder. You can see that spot there where it starts to rip the paper a little bit because it's so saturated with ink. But the key here is that this is a sphere only insofar as we can read spherical qualities in the relationships of the lines. None of these little segments are components or parts of a sphere. Here's that little area zoomed in, using slightly different parameters, more aggressively long segments in the beginning, so that the tendency to pool up is a little bit higher. I have another series of drawings that are also concerned with depth, but a different kind of depth. In this case, it's not formal depth, but atmospheric depth. So this is a pen plotter drawing from above. I didn't want to connect to the speakers because the sound can get quite annoying, but you hear it slightly, right? And so there are actually all sorts of interesting cues. Certainly, you're losing the haptic response from the paper, but you get this auditory suggestion of that material contact through the sound. And this is treating, these pen plotters, I was talking to Britt about this the other day, they were horrible if you wanted to reproduce drawings because they're not consistent. The reasons why I love them are the reasons why they were tedious to use, because the felt wears out. So that one drawing is different from the next, and the ink bleeds and it can kind of smudge. So it actually becomes possible to have this pen-plotted line drawing that has qualities of a painting, where there's no green pen used in this. This is all about mixing the colors of the ink. And the grid, which basically, as you could probably tell from the sound, is basically just a grid with rotating lines along the X and Y axis to create these patterns, resonant patterns between the ink colors. So you get an extreme depth, but you also get these ripply patterns on the surface of the paper. This is this, what I call the storm series of drawings. Imagine that there's like a sea or an ocean at the bottom and some sky at the top. The key architectural concept here, or condition, is the idea of the frame. Instead of this being like a frame that is looking into the world, in these drawings the frame is the entirety of the world. So a system of forces exists in this frame, and you can think of these as like long exposure photographs of these particle systems playing out to make storm-like conditions. Certain rules can define and assert clouds, and I really have to say clouds because it's a kind of imposed logical structure of something like a cloud, which is so artificial, it's almost unfair to make this natural analogy. But the clouds actually become, they started as a way to debug the program. They became kind of beautiful moments. They became so beautiful and so superficial and so depthy. I use ridiculous words like that, I'm sorry, depthy, but I have to. They're so depthy, very, very useful for the students. Make it more depthy. Anyway, became so interesting that looking at the clouds in isolation is quite compelling and interesting to me, because there's so much stuff that's happening to make these clouds. It kind of sustains a lot of intrigue and interest. One more storm drawing, a little more clouds. This is what happens when you draw that same exact storm, but instead of drawing the vector, which is like the difference between the particles at different states, this is drawing the links between the particles that makes them cohere as something like a fluid. Again, there are qualities of surface and time and edge. This is that same storm represented as an animation. So it's the same information as the drawing represented as an animation. You'll see some rain happen there. Again, rain. Rain is the result of an if statement that says when there's a cloud that's particularly heavy, make it rain. I have a long discourse about, I hassle my students often when they try to do something stupid like pin up code for a review, but this was for an exhibit that really wanted me to pin up the code. It was with my colleague Hina Lesky, who has a book called The Storm of Creativity. She has it's a pervasive storm metaphor. Her and I basically did this same project in a kind of, in totally different ways. We purposely didn't talk that much during our parallel processes. Anyway, this isn't the best snippet of code actually, it's quite a tedious portion, but I tried to write this code that was meaningful and it's ironic, and there are some Easter eggs and humorous moments. Like I think I'm the only one that's laughing at moments like this. But the goal was to think about, the code is an interesting window into the representation of these storms. There's actually two kinds of code though. There's the Python code, which I showed, and we're advancing kind of slowly here because I was stupid. I put this as this is a PDF file that's huge. This is the machine language code. So pen plotter art or drawing involves writing Python code to generate this machine language code, which is the thing that ultimately gets sent to the plotter. I have this in one massive PDF, and this is like a crop of it. The next slide is also quite large because what was also pinned up at the gallery was this log file, which is a narrative textual representation of the storm event. So there's the animation, there's the machine language code, there's the drawings, and it will come in a second. This is the narrative. It's about 20,000 words per drawing. I will zoom in. It's very tedious language, but it's the description of everything that's happening in that storm. So it's English language there. It says boring things like the time is now 7:93. It is cloudy. The time is now 7:94. A ball that is not part of the group is crossing the horizon. It is changing state. It is cloudy. Tedious language. The sea is tumultuous. The sky is tumultuous. Every once in a while, there's an exclamation point for irony. But this idea that this is getting back to representation and the idea that the code itself is a kind of representation, and the code is fundamentally a body of text, just like this, that can be read. So I now want to show 3 student projects and the results from those projects to help position not just why I'm interested in architectural drawings made by the computer, but how it affects how architects learn, which is extremely valuable to me to observe and to calibrate my interest in terms of students learning. So the first is this idea of a drawing assigned to a position in depth. So on the in depth. So on the first day of class, students are assigned a number randomly, of course, and of course it's computer-generated pseudo-random numbers. And they spend the first week, they've got their number, but they spend the first week making drawings, and this is their first often experience with programming at all. So they're very primitive algorithms, often with minimal human input from a mouse or a keyboard or a button click. Simple things like exploring how 2 nested loops can make a grid, that kind of thing. But then their number assignment is really a position of depth. So on the second week, student number 4 is tasked with drawing forward what was on student number 5's drawing. So without starting over, they have to read with their eyes and with their human capacity, read what's in the drawing behind, and adjust their drawing to pull that forward. So I think this might explain it a little bit better. So there's the week 1, right? Numbers 1 through 13, done without any reference to other students, and then after it's all shifted. So now, if we look at student 3 is referencing student 4, and student 2 is referencing student 3. So by offsetting these grids, we can look at them like this, where now looking at columns, we should find some similarity. So for example, let's look. This shadow is quite productive. Let's look. Actually, I think I zoomed for us. Let's look at this drawing here, which suggests maybe the idea of a very deep horizon line there. This is this student's first drawing. Her drawing became this, which is using this algorithmic construct basically, but it's able to correspond to this condition. This student was making this, and then on week 2 was looking at this, but then on week 3, this one has become this. So this one changes to accommodate that. And it's not always successful, or it's debatable the terms of success, right? So what has become a very deep perspectival condition here has been reduced to a gradient of depth there. If we look over to this side, maybe we look at sort of this row here, or even this student who has moved from this kind of field condition to seeing, there's kind of 3 zones here, to making 3 zones here, to finally making a very formal condition based on that there. We'll look over to the right. I think there's an interesting one here. These bulges encountering this diagonal become these kind of spine-like conditions here, which then influences these kind of radial figures here. So second student project is called the Active Line Project. So in the Paul Klee pedagogical sketchbook, he says line is like taking a point for a walk. And that's in the context of describing two types of lines, active lines and passive lines. So active lines are sort of, one way of thinking about this is like the line is the thing, the line is the subject. The line is moving and animate and is kind of alive with forces. A passive line is something like a contour or an edge. It's real and it's there, but it's describing a condition. It itself isn't the subject. To interpret that line is to really see through that line into the representation of something else. So the active line project is another kind of pedagogical experiment for me where instead of teaching computer programming from a procedural point of view, a kind of if-then conditional, this is teaching it from an object-oriented position where instead of describing what happens, you describe in detail the thing and its capacity to do things and interact with other things or objects. So in this case, it works perfectly with the Paul Klee active line. An object or a class in computer programming can have collections of variables and it can have a collection of actions. Which influence how it relates to the world around it or other instances of that object. So making a line class is quite exciting. A line class is very different than a function that draws a line. So in this case, the student Sunny Zhang is looking at an adaptation of a Bezier curve line class, but instead of just thinking about the curve, she's starting to think about like perpendicular lines that might be populated along that curve, and those perpendicular lines are starting to key into other moments along that curve. So it's very hard to explain, but easy to show. Lines along that curve are starting to become very dominant and very large, starting to really reach out to other parts of the curve and respond differently based on where that point is and where that curve is on the page. She realizes very quickly, like, this is a way to suggest depth and form. She starts to say there's a kind of second order of linear systems on those dashed lines. So dashed lines are made up of, or perpendicular lines are made of dashed lines, and there can be a correspondence between dashes among multiple points on this line. So now this is formal, but is now formal and a little bit material if you think about the colors as a kind of colored wrapping paper around these forms. Okay, final project, and this is going to take the longest for me to explain because the corner problem warrants a kind of hour-long lecture. For the architects in the room, this may seem a little bit reductive, but the corner problem is a fun one. The corner problem exists here in Renaissance architecture when you have, or let me just say this, the corner problem is in architecture when you have two surfaces coming together, they make a corner. And that corner can be a linear condition, two surfaces intersecting at a line. Simple enough, except there are no surfaces in architecture. Everything has a thickness, so therein lies the corner problem, where a corner can look awkwardly too thin and too small. If the two columns at two surfaces merge into one, it's sort of like you've lost a piece of both surfaces. There's arguments that from a visual field point of view, this produces a corner that is most continuous, right, and sees the colonnade as one uniform visual condition. So again, not necessarily bad. And there's a beautiful assignment, I forget her name now, but professor at UCLA has a semester-long project called the problem with the corner problem. So there's the meta problem of calling problems in the discipline of architecture. And problem is not really the right word because there are many solutions. It's sort of like a reoccurring problematic condition that is actually not a problem at all. It's quite fruitful to think about. But anyway, you have the opposite condition where the corner is too big. So the condition here is that if you give each face its ending column, the column that it deserves to end that wall, this interior courtyard volume loses its coherence as a subtracted space. All of a sudden, this is a corner that looks like two walls meeting each other instead of a corner that has been turned. So not exactly the perfect solution. Plus, look up there at those windows. The windows, you can't see it, but I promise you that there is a window above, aligned with these modules. So then all of a sudden, you can have your column, but then what to do about that window? So now all of a sudden, the spacing of the window has been violated. So now the corner wins over everything else, which seems to defy the very notion of the corner as the resolution between two things. You have some really geometrically intelligent solutions which cause their own quirky problems. Which is fun and fascinating in its rigor, despite the fact that it has produced something that is profoundly odd, but it's my favorite. The reason why I like the corner problem is that you can look everywhere in architectural history for corners. It is not, you don't have to have columns, you don't even have to have a modularized AB condition. This is the Renzo Piano Fogg Museum at Harvard. This is a situation where this is kind of a louvered facade, right? So you imagine the facade is made of these tiny horizontal elements that basically stack. They're meant to look very smooth like a surface, but when you encounter two things like traveling along like this that have their thickness, you have this problem where even if you allow them both to exist, one of them has to become dominant, right? So you either have to say like this one is the front or this one is the front, right? This one gets chopped by that, or they're offset slightly. And none of that is really acceptable if this is a building made out of smooth, infinitely thin surfaces. So what happens in this example is that the louvers twist at the last minute near the corner to become vertical so that they can meet with the least amount of depth possible. So now that corner, oddly starts to look like something like a structural column. It's definitely not, but you see how you can almost squint your eyes and see that as a structural volume embedded in there inside the surface. So the corner problem in the world of computing drawing says, okay, you've got two algorithms that create two surfaces, construct their corner. And just like in every other example in architectural history, there's you have to take a stand on what is the definition of corner. In Sunny's case here, she says, okay, the corner is not a mediator, the corner becomes a generator. So defining the corner as like a spine that emanates lines, right? And they dissipate, instead of dissipating at the corner for a friendly merge, they're born out of the corner and then become softer later. She thinks about them, that line now as an undulating like knife blade of a kind of very, very sharp condition. That gives the project certain capacity, right? So now, once she has defined computationally that corner, she can structure and design the form to accommodate other needs of that building. We had a site that was on a corner lot, of course, because I'm cruel like that. Corner condition in a corner context, needing to resolve a corner and assert a corner, because that's what you have to do. Architecture not supposed to be easy, because it's not easy. The corner starts to sponsor really strange poche conditions on the interior. So a control over that thinness leads to a kind of emergent thickness on the interior. It also means that she, and like all the students, develops a new kind of, based on conventions, but a specific kind of drawing that chops the corner. So if we look back a little bit, she has kinds of drawings like this that basically position that knife blade corner in the foreground, versus drawings like this that chop the corner on the right? So this is like a cutaway aerial perspective with the bill of the corner chopped off, or an unfolded sectional drawing that uses that corner as a hinge. So that early drawing has permeated all the way through as a generator of the form, and as a kind of basis for representation. So now shift gears slightly and close with some ongoing research related to corners and drawing thickly. So depthy and thickly are both terms that I declare as valid. So this is, there's some beautiful Carlos Scarpa corner details that basically approach the corner as a kind of flipping condition. So given an interior condition, take a portion of it and pop it out into an exterior condition. So a convex corner becomes a concave corner and vice versa. Just starting to draw corners in that way, and just draw them with these pen plotter lines that really assert a materiality at the corner. Start to look at a condition of imperfection that is not the result of geometry, but a result of the material. Something that Tom Mills said yesterday with a kind of vulgar analogy about the paper not lying there. You know what I mean? Remember that? I agree completely. And I look for places where the material of the line can start to be the thing that suggests the form. So this is using a similar kind of coded process to draw corners using a stitching machine. So the stitching machine is excellent because the line is the felt tip pens, they are material, they have substance, they interact with each other. But relatively speaking, these thread lines are much more materially substantial. They are breaking the underlying fabric with holes, and they do not take well to being broken by other subsequent lines. So what happens is that the paper, sorry, I slip into this term sometimes, the fabric, the substrate fabric, the canvas maybe as a more appropriate word, fights back, and its material shifts and buckles because it's basically the threads are gradually piling up, pushing other threads out of the way, and that fabric has a substructure to it, despite the fact that it is relatively weak. So now we're also coming back to things, totally emergent conditions like this circular shape that is the result of drawing this corner, or on the right side, using white fabric. If I had stitched one line, you wouldn't really see it in this photograph. It really takes thousands of lines to aggregate into something substantial, and you're getting now this new kind of corner that is a result of drawing a corner. So I'm going to end now, but I just want to end with an attempt at indexing all of my thoughts in a way that answers the question I posed, which is how drawings become architectural drawings. So this is a kind of collection of those conditions. Depth in a formal sense, depth in an atmospheric sense, the frame, the surface, time, text, and a fight between object, space, and paper. And in this last research, material avoidance and material reality converging together. So I end there.